Hello and welcome back to Learn It from a Layman. I am Carl Christensen. I am joined today by Cameron, and the rest of the podcast hosts are off doing their whatever they do to, actually earn money. Cameron, how's it going?
It's going well. As you will maybe hear, I have a extra robust voice today and a little bit of a sniffle. So,
all right. Well,
thank
luckily,
you, winter season, for this.
Yes. Luckily, podcasts don't spread, are not contagious. So, all right. Well, today
we have
will
a
be
podcast about that. Actually,
we have a podcast. That's right. We have a podcast. We're at the point in podcasting where essentially everything that we talk about, we can say we have a podcast about that. So, all right. Today we're going to be talking about physics. Like I said, we've had some requests, one about to do a physics podcast, and so today we're going to actually be fulfilling that, and we'll be talking about 10 questions in physics. So some of these are pretty layman questions. I think ones that maybe you've asked yourself before or that make sense to the layman, and some of them less so. We did try to get Peter on, our physics teacher, I guess you could say. He doesn't actually teach physics anymore, but he's the guest we've had on in the past that's done theory of relativity with us. He's done quantum physics with us. He is, however, having his wife is having a baby this morning, so not the ideal time to do a podcast. At least that's what his wife said. I don't know. All right. Well, let's dig in here. All right. So first question: as light from a star spreads out and weakens, do gaps form? So before we dig into the answer for this question, I guess we need to qualify some of these, I guess to a student in physics or someone that's pretty familiar, they might have a pretty good answer right off the cuff. But once again, this is Learn It from a Layman, and some of these, like I said, you do wonder, like, okay, if light is dimming, does that mean gaps are forming? Is there, space in between the light? And what was that?
The age-old question: is light a particle or a wave?
Yeah, exactly, and that's what it comes down to, right? If we, the error is in there's an error in understanding in the question itself. The gaps form between protons. Photons, and photons. Light acts like a wave, unless you measure it, in which case it acts like a particle. And so the answer here, so these questions I've kind of compiled over a bunch of different lists. So I've got answers from physicists, as you might know from listening to our podcast, between Peter and Matt. Those are the ones that we generally go to for answers in physics. Matt did our original physics podcast a few years ago. So Cameron and I tackling this does truly bring us back to our Learn It from a Layman roots, but the answers I have here are compiled from across lots of different sources. But it says the answer depends on how you look at light. However, in the most accurate approach, gaps do not form between photons. Keep doing that. Between photons. Protons, different things, it turns out. Even I know that. Gaps do not form between photons as light spreads out. Light is made up of tiny fundamental bits called photons. A photon is a quantum object. See our quantum physics podcast. So photon acts a little like a particle and a little like a wave. And so once again, you could go dig into that in our other podcast if you want to. But this goes on to explain that gaps don't form because we're talking about a wave. Light travels as a wave. Very dim light beams have larger gaps in time and space between the reception of each photon compared to brighter light beams. light from a very distant star is spread out over a very large area and become very dim in the process. The gaps between photons' reception from a very distant dim star are therefore large. It's not that there are gaps in the photons themselves, but the gaps in how they are received, if that makes sense. So says they're not spread out while traveling, rather they are spread out in time and space as they are received. So the question is very layman, the answer less so, but I think a basic understanding that, like, okay, well, the problem is that if you view it as photons, you could see, oh yeah, they are spread out, but they're not actually photons. It's traveling as light. And then the answer becomes complex when you're saying, oh, well, it's spread out in time and space. Okay, well, that's real helpful. So it goes on, it says a rough but helpful way to look at photons is that they act like waves until traveling and act like particles when interacting with matter. So, Cameron, does that make sense?
Well, time and space makes me think of force. So I would think the greater the force, the less of the gap, perceived gap, I should say, and the lower the force, the more perceived gap.
Well, this is where we get into the point where it would be nice to have someone that's a little bit more expert, but I guess probably more like the brightness. I don't know how that correlates to force, but brighter lights, obviously, if you've ever shined your flashlight up into the sky at night, if you got some dim little rinky-dink flashlight, it gets dim really quick, where a bright light, you can shine it up at the sky and it actually looks like it travels quite a distance. So yeah, I don't know if that's necessarily exactly what you're saying, Cameron, but yeah, I think the brightness from the sun, for example, is such that this question wouldn't come up. Do gaps form between the photons of our sunlight? Well, obviously no, right? But then if you're talking about stars in the distance, you're like, oh, well, I can, it looks like it's twinkling or whatever. Obviously that's an effect of the atmosphere, but yeah, just the question of like, well, why are there dimmer lights and brighter lights? But yeah, that's just a question of the spreading out effect over the course of space and time. And then as we receive it, you're only receiving photons spread out across time. So hopefully that makes some sense. And if not, we'll get Peter on later to make more sense of it.
We'll have someone fact check us and be like, oh my gosh, you guys are so wrong. This is why you should never do a physics podcast without us.
Yes. Okay. Second question. Can one bit of light bounce off another bit of light? And so this, Matt would love this question. Matt, not available also for this podcast, but the answer here would be pretty simply, kind of. That's not a simple answer, I guess. Kind of is never really a simple answer. The answer is that they do, but it's very rare. Anyway, let's get through the text of this answer here, and then we can talk a little bit about the layman aspects of it. It says, yes, one bit of light can bounce off another bit of light, but not directly. And the effect is very rare. Light is made out of photons, which we just discussed. When you turn on a lamp, the light bulb begins creating and emitting trillions upon trillions of photons. Photons are in a class of quantum particles known as bosons. We talked about bosons before in the past. Bosons are special because many bosons can occupy the exact same quantum state at the same time. Light being made of bosons is what makes a laser beam possible. We also have a podcast on lasers. I should probably stop talking about all the podcasts we have. The laser beam is a collection of many photons all in the same quantum state. In contrast, particles that are not bosons cannot occupy the same state at the same time. This is one of the effects that keeps the atoms in an object from collapsing to a single point. We'll talk about that actually a little bit later. That's one of the other questions we're going to be discussing today. The principle that dictates the non-bosons cannot be in the same state is called the Pauli exclusion principle. Non-bosons are also called fermions. The fact that bosons such as light can occupy the same state means that they don't get in each other's way. Anyway, so that's explaining what state we're getting in and kind of the background of it. Here's the actual answer. So light dominantly interacts with objects that have electrical charge. Since light itself does not have electrical charge, one photon cannot directly interact with another photon. Instead, they just pass right through each other without being affected, because they are bosons and because they carry no electrical charge. One photon cannot directly bounce off another photon. If you point one jet of water towards another jet of water, then at the point where they cross, you will get a mess of water. In contrast, if you find one beam of light that crosses another beam of light, they will just pass through each other unaffected. However, two photons heading towards each other can indeed collide indirectly. The process is like this. The photon can spontaneously degenerate into a particle with mass and its antiparticle in a process known as pair production. In this process, the energy of the photon is completely transformed into the mass of these two particles. The photon can turn into an electron and an anti-electron. Two photons head towards each other and they both turn into electron pairs at the same time. Then these particles can interact. So the layman answer is no, they can't bounce off each other. Two beams of light shining through each other don't interact. That's what the layman gets out of this answer. The far more in-depth answer is kind of, and that's based on these principles that they were just explaining about photons degenerating, and they get you to, I'm sure, parts in physics that were well beyond what anything that I'm familiar with. But like I said, this answer takes you through all of the different scenarios, and but they're uncommon, and they but it can happen. So, Cameron, anything unclear, or I guess I should say anything clear?
I was just going to say it's probably a good thing that they don't. If you think about like the amount of energy that would be banging around, that could probably be really bad for us.
Yes, if all light interacted with each other, if they are all just bouncing around, that would be bad. So all kinds of weird things would happen.
I'm happy that under only the most extreme conditions could they actually do something like that, and so that makes me happy.
Right, exactly. I had go through all the. That sounds like a movie that should be made, is some type of like light becoming, interactive. It sounds far more boring than I had it when I first thought about it a second ago. But it seems like you could go somewhere with it.
That was pretty boring. I mean, as long as it's got Sandra Bullock and that other guy.
Yes, that other guy. Channing Tatum.
Clooney,
Oh, yeah.
I'm sure it will be a hit. So.
Okay, good. All right, well, then we'll get that. All right, next question. Can you go fast enough to get enough mass to become a black hole? So in this case, Peter explained this to me when we were discussing quantum physics, and it kind of didn't. It was relativity. That's when we were talking about this, because I said something along the lines we were talking about accelerating and accelerating to the nearest speed of light, and I said, your mass increases as you get closer to the speed of light, and Peter said that's not exactly how it happens. And then he kind of moved on so that he didn't offend me, which was nice. But essentially, that's a layman's fallacy, and that's what the answer here goes through, is that it says traveling at high speed does not affect your mass, even in Einstein's theory of special relativity. It goes through the whole process of taking you through the E equals mc squared and the whole thing to show that it's not your mass that's increasing, it's your kinetic energy. And that has an effect on the ability that you have to accelerate, which is why, and very frequently, it's explained in terms of, oh, my mass is increasing, and therefore I can't accelerate more. But that's actually not what's happening. It's the resistance to acceleration is because of your kinetic energy. That's what this is essentially saying. So can you go fast enough to get enough mass to become a black hole? Well, obviously then no, because your mass isn't increasing. So it says if you define something called relativistic mass that is completely different from regular mass, then this claim could be made to look true. But your actual mass does not increase. So that's, I think, where Peter was giving me a little bit of grace, saying, okay, well, if you kind of define it a little differently, then you could say, oh yeah, your mass does increase, but that's not according to the equations that Einstein came up with. That shows that as speed increases, the kinetic energy increases, but the mass never changes. So it's not the case that if you run fast enough, you're actually getting more massive. Cameron, any questions about that one?
Well, I'm going to say that that's good that we clarified that, because if we're creating mass, then I don't think we're allowed to do that.
Right. Yeah. I thought, well, you can't create matter. That's what you can't create, right? Or maybe it's...
Yeah. Is it mass matter? Mass is a constant amount of matter. So...
Yes. All right. Well, okay. I'm glad that we cannot create black holes on accident, because that's once again the CERN, the particle collider over there in Europe that accelerates particles to near the speed of light. That would then actually be creating black holes, I believe, if we create if we're accelerating an object that to these percentages of the speed of light, and their mass was actually increasing, then it would be possible for us to accidentally create a black hole. Turns out not possible. So sorry, guys. It's a bit of a bummer, but not going to happen. Okay, next question. Do atoms ever actually touch each other? Now, this is ATOM, not ADAM, because I think I personally have seen two atoms touch each other.
I'm not sure if I would use the word touch.
Okay.
Yes, I have seen two ADAMs come in physical contact with each other.
Okay.
And I would imagine the ATOMs can also come in contact with each other. If we can split one, I would imagine two can bump into each other.
Well, so that's where this dives down the whole real quick here. It says the answer depends on what you mean by touch. There are three possible meanings of touch at the atomic level. 1, two objects influence each other. 2, two objects influence each other significantly. Or two objects reside in the exact same location. And then it goes through and talks about how that the everyday concept of touching, the layman idea of touching, makes no sense at the atomic level because atoms don't have hard boundaries, right? And that's something for us to, you got to get outside of the layman view of like, okay, well, I'm touching it. It's like, okay, well, what does that mean? Atoms are not really solid spheres. So what does touching mean? And so those three definitions are useful. It says if the first one, if touching is taken to mean two atoms influence each other, then atoms are always touching, because atoms held a mile apart still have their wave functions overlapping. So the amplitude of one atom's wave function at the point where it overlaps with the other atom's center will be ridiculously small if they are a mile apart, but they will not be zero. So influencing each other, well, then we're all touching, right? Which is kind of a creepy idea. In principle, two atoms influence each other no matter where they are in the universe. So in that way, it's all touch. So that's obviously not what we mean, and it goes through the whole. It walks down that road. It's like, okay, but let's not talk about that definition. The second definition, touching is meant two atoms influence each other significantly. Then atoms do obviously touch, but only when they get super close. And that is generally what we think of when we're thinking touching. But the problem is what is significantly? So then you have to define that term. And so the layman's concept and interaction with physics and reality sometimes becomes, it's frustrating when you start diving into the actual definitions, because then it's like, well, I know what it means when I touch something. I'm touching something right now. Why do I have to define this and define that and define that in order to just get a question answered?
I think we could break it down a little bit from what you're saying as, the game that we played when we were younger children. I'm not touching you, but you're almost touching them. That is.
Yes, exactly. When you're like, your finger like a centimeter from their face.
Yeah. I was going to say you got that. So you're not significantly interacting with them, but you could still feel their figure. Like you could feel a person very close to you, even if they're not touching you. So.
And that.
Significant, right. That would, be like more of an actual touch, but you know what I mean. It's
right. And so this is going to go through and define exactly what they mean. It says we can define the outer perimeter of the atom as the mathematical surface that contains 95% of the atom's electron mass. It should be obvious that a perimeter that contains 100% of the atom would be larger than the Earth. I don't know. What about that is obvious? With 95% of the atom's electron probability density contained in this mathematical surface, we could say that atoms do not touch until their 95% regions begin to overlap. Another way to assign an effective edge to an atom is to say that it exists halfway between two atoms that are covalently bonded. For instance, two hydrogen atoms that are covalently bonded to each other to form an H2 molecule have their centers separated by 50 picometers. And they can be thought of touching this. And this approach, atoms touch whenever they're close enough to potentially form a chemical bond. And so that's the second one. I think that's generally what we're talking about. We're talking about this atom is pushing back against that atom because of the bonds that are formed between those two atoms. And so I think that's generally what the layman is more interested in, is that second one. And the third one is saying, if the third definition here as well, if touching is taken to mean that two atoms reside in the exact same location, two atoms never touch at room temperature, according to the principle we talked at the very beginning, the Pauli, I don't know if that's how you say it, Pauli exclusion principle. Says that all atoms in our body, this principle is what keeps all atoms from our body from collapsing into one point. Apparently, though, once you in physics, when you get to these edge cases, some rules break down. It says at very low temperatures, certain atoms can be coaxed into the exact same location. It says that's known as the Bose-Einstein condensate. Okay, and that's once again well beyond my layman knowledge, but generally atoms can't be in the exact same location. So in that case, this third definition also not particularly useful, because that doesn't happen outside of these extreme edge cases. You can't have two atoms actually hitting each other in the sense of like, we're in the same location. It's we're close enough that we're interacting in a significant way. So that one was that's a good example of layman questions becoming not layman very quickly, and frustratingly so, in the sense that, like, I just want an answer, do atoms ever touch? And then you have to define the words, and then you define other words, and then you say, okay, well, kind of, but not always. But I think we got a good answer for that second definition, and say, okay, well, they're touching in the way that they interact, and when 95% of their mass is inside a particular realm. Anyway, I think that's a pretty good answer, Cameron.
I feel it's a pretty good answer. It's making me more excited for the movie I'm about to go see. I'm going to go see the new Ant-Man quantum thing.
Yes.
And so now I'm thinking, you know what? We're kind of actually talking about this stuff. And
Yeah,
then
exactly.
Pym Particle makes less sense now, talking about. So, good and bad things, I guess.
Yes. Yes. Good and bad things. Yeah, they will debunk some of our layman fun, but such is life. Okay. Next question. What happens in the gray zone between solid and liquid? This is so. I mean, we're familiar with the four states of matter: solid, liquid, gas, and plasma. Well, okay. As a layman, you're really just familiar with three. I'm only really familiar with three states of matter. That's all: liquid and gas. We hopefully, if you've taken a physics class before, or just generally aware that there is another state of matter, that's plasma. We don't interact with it unless you're, a physicist or some type of scientist that's studying that. We don't ever interact with plasma, but we know that it is a thing. But this is saying, okay, well, what about these boundary conditions between solid and liquid? And that a layman might have some familiarity with, right? And it takes the example of sand. It says some materials act like a liquid and a solid, making the behavior hard to predict. 1 grain of sand is as solid as a rock, but 1,000,000 grains can flow through a funnel like almost like water. Highway traffic, which, nightmares. I live in Southern California, so it's far more like a solid.
I was going to say, it's like that solution you can make with water and cornstarch.
Yeah,
and
probably. Yeah.
Changes on the amount of force that you apply it. If it's a very low force,
Right.
it
Right.
feels watery, but if it's a high amount of force, it's solid.
It's a solid, right? Yeah. And this talks about saying, it says a grain of sand. So a better understanding of this gray zone, this like the sand-like behavior, can have important practical applications. Like under what conditions does the entire system jam up or clog? It says we have what crucial parameters to avoid clogging. So we need to understand this zone of solid and liquid, because if we understood that completely, we'd be able to better take care of issues like traffic. Because okay, well, traffic jams up in particular situations. Sometimes it acts like a liquid, sometimes it acts like a solid, and so understanding that is useful in understanding how the material acts. So that one is just a generally trying to, this question, what happens in the gray zone between solid and liquid, is kind of just generally saying there are parameters and ways to understand how these items are going to act.
Ooh, I found the name of what I was talking about. It's a fun name. It's called Oobleck. Oobleck. Oobleck.
Oh, that's the stuff that's liquid and solid.
Yeah, it's a non-Newton, Newton fluid.
Oh, okay. Got it. Very fun. Okay, next question. When does the sky become space? This one we should probably wait until Matt's here, but I'm not going to. The official boundary between the Earth's atmosphere and space is called and now I'm going to kill the pronunciation, Kármán line? I don't know. This line lies 100 kilometers above sea level and is named after aeronautical scientist Theodor von Kármán. Aircraft generate lift due to flow of air over their wings. The air thins with increasing altitude, and aircraft must move faster to remain airborne. Von Kármán calculated that at 100 kilometers, it was more efficient for vehicles to orbit the Earth than to fly. So at 100 kilometers, aircraft would have to move faster than satellites orbiting the Earth to generate sufficient lift to stay airborne. So that is the scientific definition of when sky becomes space. I'm sure that there are kind of, what, Cameron?
You get to 100 kilometers above sea level, you just have to do some fancy falling.
Exactly. Exactly. Um, and I'm sure that there's probably more to think about than just that. And I'm sure that there's probably definitions of when sky becomes space by the dint of like atmospheric conditions or whatever. But by this is kind of like one of the ways to measure it. And I guess it is the official boundary. So, okay, next question. This one is less directly physics, but it interested me, and so I pulled this one. It says, what is Wi-Fi? We talk about Wi-Fi all the time. This is very layman because I think a lot of us interact with Wi-Fi and we don't know what Wi-Fi stands for. Some of us do, obviously, but the more important, I guess, in the physics context, it's like, well, what is that technology? Is it different than, how is it different than satellite internet, for example? It says the Wi-Fi is a wireless network which uses radio frequencies instead of cables to transmit data. So most of us, I'd probably say actually all of us that are listening to this podcast are not using satellite internet at all. Satellite internet's very slow and latent. So unless you're in a very remote area, that's not, you use cables to get your data. And then once it gets to your home, then it's your Wi-Fi signal. So in Wi-Fi, that is actually a radio frequency. And we've talked about radio frequencies in the podcast in the past also. A wireless network is not truly wireless as it's built around the source computer connected to the internet via Ethernet cable. That's what I said. So usually cables are the important way to transfer the internet. However, the computer has a router, obviously, and changes data into a radio signal that can be picked up by an antenna inside your wireless device. To prevent outside interference, the router uses a precise frequency band, just like a walkie-talkie. So when you try to browse the internet using your laptop, an adapter within the machine communicates with the router via radio signals. The router decodes the signals and fetches the relevant data from the internet through the wired connection. This information is converted to radio signals and beamed to the laptop's wireless adapter. So that is what's happening on your Wi-Fi. And Wi-Fi, by the way, stands for nothing. It is a play off of hi-fi. And it's been back constructed. It's a linguistic thing that when you try to, it's kind of a folk etymology or a back construction, and people think that it stands for wireless fidelity. It doesn't actually. Where it came from is just a play. It's a riff on a different term. Hi-fi going to Wi-Fi. So, okay. Next question. How long? Oh, this one is really interesting. And as soon as I saw this question, I'm like, oh, we're doing this one for sure, because this one, if you've seen the Star Wars one, which movie was it? The second, so episode 8, I think, or is it 9? Anyway, the one where Princess Leia is out in space and then uses the Force to pull herself back in. It says, how long could you survive in space without a spacesuit? And I know as a layman, when I saw this, I was like, well, you'd literally immediately die. And that's not the case. It says, contrary to popular belief and numerous Hollywood movies, you could survive unprotected in space for over a minute, provided you get back to medical care immediately. And then it goes through a bunch of things that you'd have to do in order to maximize the amount of time that you'd be alive and the long-term effects that you deal with. It says you need to breathe out because the breath inside you is expanding because you're in the vacuum of space. So you'd have to breathe out so that the gas inside you doesn't explode your lungs. You need to try to get in shade. I don't know how you do that. I mean, come on, you're in space. But it says you stay out of the sun because if you're in the sun, you get fried. If you're going to swell up, So the vacuum of space will cause body fluids to vaporize, causing tissues to swell up. So that doesn't say you can necessarily avoid that. That's just part of the reason that you would die pretty quickly. But just to be aware. And then you have 10 seconds of useful consciousness. So you got 10 seconds when you are out unprotected in space before you lose consciousness. Your oxygen going to your brain will be insufficient to keep you conscious after 10 seconds, but you could survive for much longer than that. Just start breathing out right away and quickly open your umbrella so that you can stay out of the sun. Yeah, realistically, obviously, it says NASA has limited practical experience with this, but from experience with training accidents, it says that the injuries you sustain actually can be reversed, and if astronauts are returned into a pressurized oxygen environment within 90 seconds, they have a reasonable chance of living. So, anyway, that's I thought that was pretty interesting. Cameron, any insights on that?
I still don't want to try
it. Good point. I don't know why you would necessarily be interested, but I do think that I thought the whole scene with Princess Leia using the Force and surviving out there after her spaceship is blown apart was entirely impossible. I mean, I guess you could argue in the whole fact that she used the Force to pull herself back, it is entirely impossible. But if you just accept that the Force is real, the rest of it might be possible.
Now it just becomes highly improbable.
Exactly. Exactly. That's fun. Okay, next question. This one I liked a lot, and so we got 2 more. This is, by the way, 10 questions. We've got 10 questions, so we're on question number 9 coming up here now, and this one I think the layman is very interested in, and this has got a reasonable answer. One better than a lot of the very verbose answers I've seen in the past, which are nightmares. This one is why does time seem to flow only in one direction? Like not the band One Direction, but like one direction. Okay. Why does time go one way? And like I said, I think most people are interested, like why, and trying to come up with it. And sometimes you come across this very wordy article that doesn't essentially end up saying anything particularly useful. This I thought was a pretty succinct, useful answer that makes a little bit more sense to me. It says, physicists have thought of space and time as forming a 4-dimensional structure known as space-time, but space differs from time in some very fundamental ways. In space, we're free to move out as we wish, obviously. When it comes to time, we're stuck. Time, unlike space, seems to have a preferred direction. Physicists call it the arrow of time. Some physicists suspect that the second law of thermodynamics provides a clue as to why. It states that entropy of a physical system rises over time. So we talked about the laws of thermodynamics before, and so this is one of the implications of one of them is that if, as the law states, the entropy increases, then time has to move forward in order for that law to be satisfied. So, it says, if you have a broken teacup, which has more entropy than one that is intact, and so if time could go either way, then entropy would be decreasing as you go backwards, and that would violate the second law of thermodynamics. Entropy may be rising now because it was lower earlier, but why was it low to begin with? Was the entropy of the universe unusually low 14 billion years ago when the Big Bang brought it into existence? It says for some physicists, including Caltech's Sean Carroll, that's the missing piece of the puzzle. If you can tell me why the universe had a low entropy, then I can explain the rest of it, he says. In some physicists' view, entropy isn't the whole story. So, one physicist, Whiteson, said to me, the deepest part of the question is, why is time so different from space? So it's unclear exactly why some of these preconditions are met. The second law of entropy to explain the one directionality, the one wayness of time. But I thought it was more useful to understand, like, okay, but according to the second law of thermodynamics, there might be a reason for time to only move forward. And then there are still other questions to answer about, well, why are we in that state? Anyway, but kind of useful, right, Cameron? I'll take by your silence you didn't find it particularly useful.
I don't know. It hurts to think that, because that's another strike in my head that time travel will never happen.
I know, it's sad.
Time travel, I should say. Forward time travel happens all the time, just not travel.
Yeah, exactly. The idea of moving around when time goes from being a river to being a lake, that'd be fun. But not so much.
Not so much.
Yeah.
Okay. Yeah. It's sad.
All right, last question. Are there additional dimensions? So I'll read through the answer here. The layman answer is, well, not that we can measure, at least not that we've measured yet. However, the more nuanced answer is possibly, and that might explain some of the things that we can't yet explain in physics. So this answer, it says to get to that place, we might first wonder if nature is in fact schizophrenic. Should we accept that there are two kinds of forces that operate over two different scales? Gravity for big scales like galaxies. The other three forces for a tiny world of atoms. So we're talking about the fundamental forces. And unified theory proponents say that there has to be a way to connect the atomic scale, the strong force, the weak force, and gravity being the big force. What is that fourth force? I can't. Cam, look that up for me really quick. I know we talked about this in one of the podcasts, but I keep saying that. I'd actually like to give the information. There are three atomic scale forces, and then there's gravity. Anyway, but the unified theory proponents say that we need to be able to connect all those forces into one unified theory, and that's not easy. Einstein's general theory of relativity says gravity isn't so much a force as it is an inherent property of space-time. Accordingly, Earth orbits the sun not because it's attracted by gravity, but because it has been caught in a big dimple in space, time caused by the sun. Yeah, shoot.
The strong force, the weak force, the electromagnetic force, and the gravitational force.
Okay, the electromagnetic force. That's what I was missing. Thank you. Strong force, weak force, and electromagnetic force. Those are the ones that at the quantum level we can study. But in our layman view, we don't. I mean, that goes back to this whole touching question. It's like, well, I can understand gravity, but strong force, weak force, and electromagnetic force, I don't really understand at the layman level. But if I'm touching something, I'm touching it. I don't want to have to define, like, okay, well, what is all those forces and how they interact. But according to the unified theory of physics, we should be able to put these all together in one bucket, but that's really difficult. And Einstein says, well, gravity might just be different. And so it says, secondly, gravity, as far as we've been able to detect, is a continuous phenomenon. So the other forces of nature come in discrete packets, right? So all this leads us to the string theorists and their explanation for gravity, which includes other dimensions. So the original string theory model of the universe combines gravity with other three forces in a complex 11-dimensional world. In that world, our world, 7 of the dimensions are in that world, meaning our world, 7 of the dimensions are wrapped up on themselves in unimaginably small regions that escape our notice. One way to get your mind around these extra dimensions is to visualize a single strand of spider web. To the naked eye, the filament appears to be one-dimensional, but at high magnification, it resolves into an object with considerable width, breadth, and depth. String theorists argue that we can't see extra dimensions because we lack instruments powerful enough to resolve them. So, and that we might not ever be able to get at these extra dimensions because direct evidence of their existence it doesn't exist. But who knows? So that's the question. The answer to that question, though, from the layman's point of view, then are there additional dimensions? Is not that we know of, and that maybe this 11-dimensional world exists. But I mean, if you can't show me in the world of science, then there's no point in talking about it. So unless you can somehow use it to prove something and give me concrete evidence, then let's not spend our time spinning up extra dimensions just because it's fun. Though I guess that's exactly what the Marvel Universe is doing. Okay, those are our 10 questions, and hopefully we've kind of dealt with them in a accurate way, if still a layman way. Cameron, any last final thoughts on physics or any of these questions before we wrap up?
I just looked at a simplified version of the 11 dimensions that we live in, and it hurts my head.
Yes, well, turns out 4 dimensions kind of hurts your head. And so I can only imagine that 11 is just the best way I've ever understood extra dimensionality is multi-dimensional arrays in computer science. But that won't help most of you. And it is only anyway, it's, yes, for our day-to-day interactions, it is,
when I got to the 7th dimension, that's when it really started to hit. I was okay up to the
so 6 dimensions you're okay with. It's that 7th one that ticks you over the edge. Huh?
Yeah, it takes me over the edge. Like I understand what they're talking about till there, and then I'm like, oh my gosh, this.
Oh. All right. Well, there you have it. According to the unified physics theory of physics of Cameron, we got 6 dimensions, and the 7th one is too much. I love it. I'll stick with my 3-dimensional world.
And apparently the 10th dimension is just a point.
Just a point.
Just a point.
All right. Well, on that note.
Makes no sense, but okay.
All right. Well, thanks, Cameron. Hopefully these questions and answers were useful and insightful. And we will have on our next physics podcast, which we'll do in the not too distant future because it is what a lot of you come to this podcast for. We'll have Peter on, we'll have Matt on, we'll have some other guests on here in the not too distant future, also to discuss more about electricity. And we've got some interesting ones here in the near future, but hopefully you've learned a little bit about physics from this podcast and some of the answers, and we'll be back again soon. In the meantime, please go on and give us a rating on Apple Podcasts. That's the one that we have a lot of followers on Spotify. But from what I understand, which is from practical experience, there are a lot of people that listen to podcasts on Apple Podcasts, and most of them don't listen to us. So if we had more reviews, more people pointing people in that direction, then maybe we'd be able to get that added dimension right there. But
there we go.
However you consume get go ahead and share us. And if you have any questions or any requests for podcasts, send us an email. Hit us up on Facebook. We'll be back again soon. Thanks.